Today we're going to look at energy for rotating objects. We know the kinetic energy of an object is 1/2 mv squared from earlier in the year. I didn't really talk about it at the time, but that's the kinetic energy of a point mass that is not rotating. Now, if we have a rotating object, total kinetic energy of the whole object would be equal to the sum of the kinetic energies of all the individual particles that make up the object. So we can just add up all the 1/2 mv squareds. Now we know for a point on a rotating object, we can say that velocity is equal to r omega, which leaves us, and omega is constant throughout a rotating object, so we can pull the omega squared out of the sum, and the 1/2 is also a constant, so we can pull that out of the sum as well. And when we add up all the mr squareds for the particles that make up an object, this is the definition of moment of inertia. So rotational, the kinetic energy of a rotating object we can say is 1/2 I omega squared, which is what we would expect because the rotational equivalent of mass is moment of inertia, the rotational equivalent of velocity is angular velocity. Now, unlike potential energy, where we had gravitational and spring potential energy, there are two different kinds. There are other kinds, chemical potential energy, etc. This is not a different type of kinetic energy. It's a description of the total kinetic energy of all the particles that make up an object, but it's still the same kinetic energy. There's nothing different in concept about it. This is just a formula we can use that is equal to the sum of all the 1/2 mv squareds for everything that makes up a rotating object. If we have a hollow cylinder and a solid cylinder with the same dimensions, they're made of the same material, rotate with the same angular velocity, which is greater kinetic energy. Well, if we have the same angular velocity, then kinetic energy is dependent on moment of inertia. So we know kinetic energy is 1/2 I omega squared. Angular velocity, omega, is the same. So kinetic energy depends on the moment of inertia. And in this case, if they have the same dimensions and made of the same material, then we can say that the solid cylinder will have a greater moment of inertia because the solid cylinder is a hollow cylinder plus more material. Thus, the kinetic energy of the solid will be greater than the kinetic energy of the hollow. In this example, a tennis ball with mass m and radius r is moving through the air at speed v. It's rotating it at such a rate that its angular velocity is v over 2r. Find its total kinetic energy. Now, I just wanted to take a moment to point out that we use the relationship omega equals v over r. That's true for a point on a rotating object, or for the center of mass of an object that is rolling without slipping. But if an object is just moving through the air, the motion of its center of mass and its rotational motion are kind of just independent of one another, so they can have any relationship that you want. So this ball is both moving and rotating, so its total kinetic energy is going to be 1/2 I omega squared plus 1/2 mv squared. Tennis ball, closest approximation for that is a hollow sphere. Hollow sphere has a moment of inertia 2/3 mr squared, and I said that omega is v over 2r squared, and then translational kinetic energy is just 1/2 mv squared. R cancels out, factor of 2 cancels out here, And we have a third times a half squared. That's a third times a fourth, which is a 12th. 1/12 mv squared in that first term, 1/2 in the second term. 1/2 is 6/12, so the total is 7/12 mv squared. Here's another example. Merry-go-round has mass 230 kilograms and radius 1.5 meters. A child with mass 38 kilograms is on the merry-go-round 0.89 meters from the center. His father pushes the merry-go-round, giving it an angular speed of 5.8 radians per second. What is the total kinetic energy of the merry-go-round and the child? Well, this is all a rotating system, so we can say the total kinetic energy is 1/2 total moment of inertia times omega squared. The best approximation for merry-go-round is solid cylinder, so we can say that that moment of inertia would be 1/2 mr squared. And the child moving around, the child is moving in a circle but not spinning, so the child can be approximated to be a point mass, which has moment of inertia mr squared, and then we can plug in the numbers that were given to calculate the total kinetic energy of this system. So 0.5 times 230 times 1.5 squared plus 38 times 0.89 squared times 5.8 squared. And we get that it's about 4858 joules. Okay. It's a little calculation warning. It says beware the double square. Well, what I mean by that is the formula I omega squared. That's the formula for kinetic energy of a rotational object. But the moment of inertia also usually has an r squared or an l squared inside that. So just make sure you square both that r and the omega. That's a common calculational error.